Hello everybody, am I audible guys? Hello everybody, am I audible guys? हेलो सर, बच्चों को इंटीमेट नहीं हुआ था क्या मैसेज? एक सेकंड रुकना सर, क्योंकि आपने आपने शायद वो डाला है, टेलीग्राम का लिंक, चैनल का लिंक डाला है बस शायद। हाँ जी, मैं तभी करूँ, बच्चे आए नहीं हैं। हम्म। क्या करें बताओ सर। हाँ बट बच्चों का एक भी मैसेज नहीं आया। आई थिंक बच्चों को लगा नहीं पता। हाँ जी। नहीं, अभी मैंने कुछ नहीं डाला, मैंने सोचा आपसे कंफर्म कर लूँ एक बार में। सर एक, आपकी आवाज़ प्रॉपर नहीं आ रही है मुझे, मैसेज करिए सर मेरे को ना, व्हाट्सएप पे करते हैं अपन। मैंने कर दिए सर, लाइक कर दिए। हाँ जी। ठीक है सर, ठीक है। ओके सर, ओके। ठीक है सर। ओके सर। गुड इवनिंग करुण्या, मेरी आवाज आ रही है आप तक? एम आई ऑडिबल टू यू? गुड इवनिंग विष्णु, एम आई ऑडिबल गाइस? Good evening, Vishnu. Am I audible, guys? Okay. Okay, great. So, we will wait for 1 minute so that everybody can join our class, because this is the first class, I'll say, for the chemical reaction engineering, or you can say for the remaining parts only, right? And so we'll wait for others to join our class. Good evening, Karunya, Vishnu, Devash, everybody. Good evening, very good evening, all of you guys. So successfully we have completed our solution thermodynamics previously. Now I will take your remaining part of the CRE. Okay, I will take your remaining part of the CRE. So in the CRE1, two major topics are remaining. That is your non-ideal reactors and your non-isothermal reactors, right? So these two, if I'll say that my chemical reaction engineering is of the weightage of the chemical reaction engineering in the GATE is 10 to 12 marks. It may vary year to year, right? So let's suppose it's किसी पेपर में किसी ईयर में ये 12 मार्क्स का आता है. So I'll say that 8 marks is of your CRE1 and 2 to 4 marks is basically your CRE2, only the catalysis part, right? In the CRE1, that 8 marks I'll divide the 4 marks in the up to the ideal reactor kinetics, and the 4 marks is basically related to the non-ideal reactor and the isothermal, non-isothermal reactors, right? So these are the bifurcation actually. So you can say that the whatever your part is done till now for the CRE1, that is your 50% part in the marks context, right? And the remaining part will be the non-ideal reactor and the non-isothermal reactor. We will discuss that, okay? So and there is due to some miscommunication, your class will be actually we couldn't intimate you the masses, guys. So for that बहुत आपसे माफी. Good evening, Maina. Okay. So today we will discuss the non-ideal reactors. First we will discuss the non-ideal reactor. After that we will discuss the non-isothermal reactor. After completing your CRE1, we will move to the CRE2, and whatever the remaining part is, we will discuss that part. Okay. Okay. Tell me, semi your semi batch reactor is done. Semi batch reactor is done, guys. Semi batch reactor is done, guys. कोई बता सकता है? Can anybody tell me, Mahina, semi batch reactor is done or not? Okay. So guys, okay, ठीक है. So CRE is my one of the favorite topic, I'll say, because this is the heart of the chemical engineering, right? Without chemical reaction engineering, we are not the part of the chemical engineers. Every subject, or you can say most of the subjects, you will say like your the fluid mechanics, you'll see your thermodynamics, you'll see your IPC. These are the subjects which other branch students also study those subjects, but CRE is only one. You can see heat transfer also. That is the part of the part of the curriculum of your mechanical guys, right? But CRE is one of that part which is your purely for the chemical engineers. It is purely for the chemical engineers. Okay? So that's why I love this subject. Also, the weightage of the CRE is very, very high as compared to other subjects, I'll say, in the GATE examination or in the other PSU's examinations also. That's why this subject is very important in terms of concepts, in terms of your weightage, in terms of everything, in terms of interview also. This subject is a very, you can say, crucial, or this subject is very, very important, right? If you will say the CRE is your one of the your favorite subject in the interview, that also will impact the interviewer, because CRE is the core part of the chemical reaction engineering. That shows that you are basically technically sound in the context of chemical engineering. Okay. Good evening, Anushka. Right. So that's why I like this part. Now, so your CRE1, half of the CRE1 means till the kinetics of the your ideal reactor. That is till that chapter. I think that part is done. Or you can see your ideal reactor is done, right? Non-ideal reactor is somehow connected to the ideal reactors. I'll use the information of the ideal reactor parallelly for the non-ideal reactor study, right? Guys, आपको सबको पता है कि मेरा पॉइंट ऑफ व्यू समझाने के, क्वेश्चन सोल्व करने के साथ साथ मेरा है कि आप कोर कॉन्सेप्ट को समझें, है ना, कोर कॉन्सेप्ट को समझें. ये मेरा एक, अब आपको पता है कि एक हमारा वे रहता है सब्जेक्ट को समझने का. I have to use some ideal reactor information, and you have done that part from other teacher. So for clarity purpose, I'll ask some one or two questions. That questions are actually required for the designing of the non-ideal reactor. Okay. So good evening Kia. So I'll ask some questions in between so that मेरी तरफ से assurance ये हो जाए कि ठीक है कि आपको ये पता है. And based on that context, I can move for the non-ideal reactor. Okay. So let's start the class, guys. So once again, good evening all of you, and this is our first class of the chemical reaction engineering, in which we will study the non-ideal reactor. Right? Okay. So see, non-ideal reactor. So, and we have done the, basically we are aware about the ideal reactors. First of all, let's understand the difference between the ideal reactor and non-ideal reactor, right? That difference is very, very important for us. Okay. So we will discuss the difference between the ideal reactor and non-ideal reactor. Let's understand this, guys. Okay, समझते हैं इसको. Let's understand this. See, guys, ideal reactor definition is something like that every molecule should span the equal residence time. Residence time means the time basically spanned by the molecule within the reactor, right? You know this. This is the definition of the residence time. So what I'm saying about the ideal reactor, I'm saying that every molecule should spend the same time within the reactor, or every molecule has the equal residence time, right? Equal residence time. Is it clear to you? So this is my ideal reactor. On this earth, there is nothing like ideal reactor. Ideal thing is only our assumption. Actually, whatever you studied in the ideal reactor, that you studied for the designing of the non-ideal reactors, so that you can understand the non-ideal reactors. Because in the industry, in the you can say practical world, in the industry, all the reactors are non-ideal. So to understand the behavior of the non-ideal reactor, you should have the knowledge about the ideal reactor. So as you know that non-ideality is not the good thing for us. Everyone wants to be ideal, and everyone basically follows their ideal. है ना? आपके भी ideal होंगे कोई. You want to follow those, right? So that in a similar way, non-ideal reactor also basically want to be like the ideal reactors, but there are certain reasons. That's why those are the non-ideal reactors, and they have to deal with it, right? Is it clear to you? So ideal reactors are, you can say, are ideal case. So if these are the ideal case, means that certain assumptions are we assumed, right? Certain assumption we are assumed. So in that certain assumption wala part, one assumption, or you can say one of the assumption is that every molecule spend same time within the reactor. Or you can say every molecule has equal residence time. Right? In the non-ideal reactor, I'll say that every molecule spend different time within the reactor. Or we can say every molecule has different residence time. Let's suppose this is my ideal reactor. And this is my non-ideal reactor. Okay. Let's suppose, guys, one molecule enters in the ideal reactor at 5 p.m. I'm taking some random example so that we can connect to this definition. So a molecule is basically entering into the reactor at 5 p.m. and it is exiting to the reactor at, let's suppose, 8 p.m. And another molecule entering to the reactor at the 6 p.m. right? And it is exiting to the reactor at the 9 p.m. And one reactor is entering to the reactor at 4 a.m. and it is exiting to the reactor at 7 a.m. right? So every molecule spends same time within the reactor. It doesn't mean then every molecule should enter to the reactor at the same time. No, that entering time can be different, right? Because these are the continuous reactors, so continuously your input is going on. So some part of your feed is entering at some point of time, and other molecules entering at the different point of time. But the residence time, the time they spend within the reactor, that is the same. As in this case, you can see that this molecule spent the 3 hours in the reactor. Also, this molecule spent 3 hours, 6 to 9, right? 3 hours. Also, this third wala molecule also spent 3 hours. So this is basically our assumption, you can say. Okay? This is basically the assumption, you can say. So these are the three molecules, you can say, and all these molecules are spent 3 hours within the reactor. So we will say that this is my ideal reactor, because this is the assumption for the ideal reactor, right? But in the non-ideal reactor, guys, what will be the case? Let's suppose one molecule entering at the 5 p.m. and exiting at the 8 p.m. One molecule is entering at the 6 p.m. and it is exiting to the 6:30 p.m. One molecule is entering at the 4 a.m. and it is exiting to the, you can say, next day 4 a.m. right? Next day 4 a.m. right? चलो 4 रख देंगे तो आपको हो सकता है कि समझ में ना आए. And let's suppose it is exiting to the reactor at the 1 a.m. right? Okay, so as you can see here that this molecule spends the time within the reactor 3 hours. This spends only 30 minutes. This spends only 30 minutes. And this spends only so many hours. ठीक है? Approximately 9 hours. Sorry, not 9 hours. 24 minus 3, 21 hours. Right? You can say so many hours. Or you can say the long time. You can say the long time. As usual, long time. So it means that every molecule spends the different residence time, different time within the reactor. Why? Because there are the known ideality into it. Because there are the known ideality into it. I hope that this is clear to you. I hope that this is clear to you, right? This is clear to you. So this is the difference between the ideal reactor and the non-ideal reactor. This is the difference actually. I hope that this is clear to you guys. Bolo. I hope that this is clear to you. Yes or no? Tell me. Tell me that this is clear to you or not. Till now it's clear to you. Okay, great. So हाँ जी, okay, ठीक है. Now see. Now we designed the ideal reactors, right? You have the your designing equation for the MFR, you have the designing equation for the PFR and all that. You have the designing equations, guys. In the designing equation, what is the relation? In the designing equation, there's the relation between your time versus your concentration or time versus the conversion. Is it clear to you? Is it clear to you? So basically you designed or you basically वो जो design equation आप निकाल पाए, you are able to calculate the designing equation. Why? Because you have the data of the time. Because you have the time data for each and every molecule. That is the same for all. Is it clear to you? But in the non-ideal reactor, we don't have the time for each and every molecule. Every molecule spends the different residence time, different time within the reactor. So it is you can say very impossible to calculate the residence time for every molecule, guys. Every molecule, right? Is it clear to you? So that's why it is very difficult to design the non-ideal reactor. Why? Because we don't have the kinetics. We don't have the kinetics, guys. We don't have the design. We don't have the design because we don't have the data of the time. That is very very important for us. जब टाइम का पता लगेगा तभी तो हम वो कमेंट कर पाएंगे कि कितना रेजिडेंस टाइम उसने वहां पे रहे एंड कितना कन्वर्ट हो पाया वो. Right? So in the non-ideal reactor, we don't have the data of the kinetics. We don't have the data of the design. Is it clear to you? So this is basically problem for us. This is basically the problem for us, right? Is it clear to you? Now, so we will try to pick up one parameter. Based on that, we will try to build the non-ideal reactor designing. And we will try to understand the non-ideal reactor. We have to pick up one, you can say, the parameter, right? So now tell me one question from the CRE-I. Tell me guys, what is the back mixing? What is the back mixing for the PFR and what is the back mixing for the MFR or CSTR? Tell me. In this chronology, what is the back mixing of the PFR and what is the back mixing of the MFR? बोलो बोलिए. If you don't know, no worry, just say no sir. ठीक है, just say no sir, we don't know. अगर नहीं पता तो आपको मना करना है, that's it. Zero for PFR, infinity for MFR. Okay, great. Zero for PFR. Okay, zero for PFR, infinity for CSTR. Okay, great, great, very good, very good. बहुत अच्छे, बहुत अच्छे. Yeah, very good. So back mixing is zero for the PFR and it is infinite for the MFR. Means there is no back mixing in the PFR. There is no back mixing in the PFR. PFR has a flat velocity profile. PFR has a flat velocity profile. There is no back mixing. And in the MFR, there is a infinite back mixing. So back mixing is that my parameter. Based on that, we will try to understand the non-ideal reactor. Right? Now understand this. So if we will talk about the ideal reactor, guys, if we will talk about the ideal reactor, just understand it, right? ये बहुत ही समझने वाला part है. If we will talk about the ideal reactor, so we have two ideal reactor, right? And considering that every molecule spends the same residence time. So one is my PFR and PFR is look like this. PFR is look like this. This is my PFR. And one is my MFR or you can say CSTR. So this is my MFR or you can say your CSTR. And this is your PFR, right? These are the ideal reactor considering a point that all the molecules spends the same residence time. PFR has the zero back mixing and I'm talking about in the context of back mixing. PFR has the zero back mixing and your MFR or CSTR has the infinite back mixing. So these are the 2 points of the ideality, or you can say these are the two extreme point of the ideality. That PFR has the zero back mixing and MFR has the infinite back mixing. So back mixing is a point. So whatever the value is of the back mixing, for sure that is lies between the 0 to infinity. For sure it is in between the 0 to infinity. Yes or no? Yes or no? Is it yes or no? Is it clear or not? So guys, non-ideal reactor is basically whatever the back mixing is, that back mixing is basically in between the 0 to infinity. Yes or no? So whatever the value we have of the non-ideal reactor back mixing, that is in between the 0 to infinity. So we design the non-ideal reactor in between the PFR and the MFR. In between the PFR and the MFR. Is it clear to you? This is my non-ideal reactor. Sir, why you draw this random structure? Because we don't know the designing. We don't know the designing. That's why I draw its random structure. I don't know what is it. I don't know what is it. I hope that this is clear to you. I hope that this is clear to you. Yes or no? So from 0 to infinity, in between a non-ideal reactor designing will be there. Means the non-ideal reactor is existing between the PFR and the MFR. It is existing between the PFR and the MFR. Is it clear to you? Yes or no? Right? So guys, non-ideal reactor is basically, you can say that Non-ideal reactor is combination of, it is the combination of ideal reactors, right? It is basically combination of the PFR and MFR. I hope that this is clear to you. It may be possible that, let's suppose we have this non-ideal reactor in which this is V is the total volume. This is the total volume V, and out of which this is the V1 volume, this is the V2 volume. So it may be possible that V1 volume is behaving like MFR and V2 volume is behaving like PFR. Because it is a combination of the ideal reactors. Non-ideal reactor is basically existing in between the ideal, PFR and the CSTR. I hope that this concept is clear to you guys. समझो बोलो. Correct, yes or no? I hope that this thing is clear to you. बोलिए, मेरी बात सबको समझ में आ रही है इतनी? This thing is clear to you or not? So we will pick a back mixing. Now based upon the back mixing, we will try to design the non-ideal reactor, guys. We will try to design the non-ideal reactor. And non-ideal reactor is nothing. If you pick the back mixing, then it is in between the PFR and the CSTR, or we can say it is the combination of the PFR and the MFR. Then you will say, sir, it's something like that, it is something like that in a pipe. In a pipe, there is a MFR and there is a PFR. You are trying to say this? No, guys. I don't want to try. I'm not saying this. Because these CSTR, PFR, all these are in our head. These are nothing. These are only the flowing behavior. When you designed the ideal reactors, so that there are 3 to 4 parameters. Based on that, we designed the ideal reactors. If you remember, out of which one parameter is the flowing pattern. What is the flowing pattern? Based on that flowing pattern, we decide that okay, this is the flowing pattern. Now we will say this is the CSTR. And if this is the flowing pattern, I will say this is the PFR. Right? So that structure, that the thing, we basically give it to understand all the things, right? So this is nothing like that. This is the nothing like that. कि एक pipe के अंदर दोनों ही हैं. No. This is the only behavior. That V1 volume behaving like the MFR and V2 volume behaving like the PFR. In the context of the back mixing. I hope that this is clear to you. Now, coming to the non-ideal reactor, that how it is the combination of the ideal reactors. Okay. Now, let's understand this, guys. Let's understand this. Just listen me and carefully listen me. And if you have any doubt, if you face any difficulty, just batao mujhe, let me know. Okay. Now, how, sir? How understand this? That it is the combination of the ideal reactors. And in what case we will say that okay, this is the perfect combination of the PFR and MFR of the non-ideal reactor. Okay. So let's suppose I have a non-ideal reactor. This is my any non-ideal reactor. If I'll making any random structure, it means that this is my non-ideal reactor. So in this non-ideal reactor, guys, there is any input. This is my input, and let's suppose the total volume of this reactor is, let's suppose 20 liter. It is my total volume. So I hope that you are aware about it. चलो मुझे बताओ, ठीक है, मुझे बताओ aware about it क्या पूछना चाहिए मुझे. Tell me, guys, what are the 2 output parameter for us while designing the ideal reactors? What is the output? If you design something, you are getting, if you want to get something now, what is that? Tell me, what is the output in the ideal reactors designing? No, no, no. I'm talking about the designing. I'm talking about the designing perspective. Conversion. Okay. Anything else? Anything else? Conversion. Okay. Anything else? Purity. Okay. Okay. Anything else? Flow rate. Flow rate. Flow rate and concentration. Space time. Okay, now understand. See, when I'm talking about the designing, then there is no point of purity and all that. Okay, there is no point of concentration and purity. These are all the kind of product things. Purity can be changed, right? And it is totally depend upon that what product I basically form, what purity I want, what is the purity required in the market. So these are the other things I'm talking about in the designing perspective. So guys, basically the designing perspective is your volume of the reactor. Your volume of the reactor. Is it clear to you? Actually, see, I will make it easy for you. A manufacturer come to a designing company and he'll give the all the parameters that these are the parameters and I want this conversion. I want that this much of conversion I want to get from my product. Is it clear to you? So basically for the conversion, the design engineers basically calculate the volume required also. Volume required for the reactor. So we basically, if we will talk about the output, then we will talk about in only two terms. One is the conversion and one is the volume. One is the volume. Is it clear to you? Because let's suppose somebody is giving us a value, okay, I want to get my conversion 98%. But when we will designing that 98% conversion requires a very large volume. उतना स्पेस उसके पास है ही नहीं, उतना ऑपरेट करने की कोस्ट उसके पास है ही नहीं. Volume of the reactor means the cost actually, the space cost actually, the running cost actually, the maintenance cost actually, बहुत सारी cost उसके अंदर ऐड हो जाएंगी. So basically this is a trade off between the conversion and the volume, right? So this is a trade off. जहां पे सेट होगा कि okay, this is the volume required, I can bear that, and this is the conversion, I can bear that. Okay, this is my designing. So the designing output is my volume or my conversion. That's why in the designing equation you are using the design equation V upon F A naught is equal to dx upon Rx, like that. That we basically that person gives me the conversion value. I repeat the back calculation by assuming the volumes. I'll keep the volumes value and calculate the conversion through the designing equation. Okay, 3 liter CST are giving me this conversion, 4 liter CST are giving me this conversion, like that. Right? Is it clear to you? Or you can also reverse the calculation by putting the conversion, you can get the value of the volume. So volume and conversion are the output of the designing, not the concentration, space time, purity and all that. Okay, is it clear to you? Now that's why here I'm talking about in the volume. So if my non-ideal reactor is my 20 liter, this is my, let's suppose this is my 20 liter non-ideal reactor, and this 20 liter reactor giving me some output, guys. It is giving me some output. Let's suppose this output is my O1. Like this is my reactor and let's suppose it is my output O1. Okay, I'm saying that this is the combination of the ideal reactor. It means for sure this reactor. Now see, हिंदू माइथोलॉजी के अंदर हम क्या बोलते हैं, दैट आर गॉड विष्णु इज द अवतार, और यू कैन से ना, उल्टा बोल रहा हूं, योर श्री राम और द श्री कृष्णा, ये क्या बोले गए हैं, दीज पीपल आर अवतार ऑफ द विष्णु जी, राइट, दीज आर द अवतार ऑफ द विष्णु जी, है ना, विष्णु के अवतार हैं. सो इसके अलग अलग मतलब हो सकते हैं. देर आर डिफरेंट यू कैन से मीनिंग ऑफ इट. One meaning from my context is that the properties, the characteristics of the Sri Ram and the Sri Krishna is very similar to the Lord Vishnu. That's why we will say okay, ये अवतार है. ऐसे ही बुद्ध में भी है ना, उनको भी अवतार बोलते हैं, शिव का अवतार बोलते हैं, है ना, बिकॉज दे वो बहुत ज्यादा योग करते थे, तो उनकी फिलॉसफी वैसी है. तो मीन्स if the characteristic, if the properties are very similar to anything, तो हम बोल देते हैं कि ये उसकी रेप्लिका है, ये उसका एक अवतार है, kind of thing, right? So I'm saying we have to design the non-ideal reactor through the ideal reactors. So हमें ideal reactor एक अवतार बनाना पड़ेगा जो कि हूबहू non-ideal reactor की तरह हो, तभी हम बोल पाएंगे कि that this is the equivalent to this non-ideal reactor. So I'm making here PFR and the CSTR, guys. I'm here making the PFR and the CSTR. So this is my PFR and the CSTR. This is my PFR and the CSTR. This is the combination. This is the combination, right? Is it clear to you? So there is any input. There is any input into this system, and there is any output into this system. So this is my combination of the PFR and the CSTR. But random, you cannot say any random combination of the reactor, that this random combination of these reactors are equivalent to this non-ideal reactor. We cannot say. We cannot say. Right? Okay. So in what case we can say that these combination of the PFR and the CSTR is equivalent to this 20-liter non-ideal reactor. I know the kinematics of this PFR, I know the kinematics of the designing, kinetics, everything for the CSTR, then it is easy to basically designing the non-ideal reactor. That's why I am picking a back mixing, so that I can design this non-ideal reactor with the help of this ideal reactors, because I know the information about the ideal reactors. Now come to the point that why, in what case I can say that this is my combination of this 20-liter non-ideal reactor. First of all, the input must be same. This is very obvious. This input must be same, guys. Right? For same input, if I'm getting the same output, then I can say that these are the right combination to show this 20-liter non-ideal reactor. Right? Now let's understand. Let's say I'm saying that this 20 liters non-ideal reactor has a back mixing 10. Let's say. Okay? And this is only an example. You cannot measure your back mixing in numbers 10, 11, 12. There's no point. This is only the example. ठीक है, जिससे आपको it will be very easy for you to understand these things. Okay, ठीक है. This is the 10 back mixing. So I want and this is, PFR has a 0 back mixing, CSTR has an infinite back mixing. If I combine these, so I'm getting any back mixing in between the CSTR and the PFR, right? And that back mixing must be 10. That back mixing must be 10. Is it clear to you? Is it clear to you? Let's suppose, guys, I have this PFR is 10 liter and this CSTR is also 10 liter. Clear? By this combination, let's suppose I am getting back mixing this 10 liter plus 10 liter. Are you guys able to see it? Okay, मैं दूसरी slide पे जाता हूँ. This is very interesting actually, right? If you attend the first 2 class religiously, then you will not face any problem in the non-ideal reactor. Every terminology, every question is something like that कि आपको लगेगा कि हाँ क्वेश्चन क्या कहना चाहता है, किस तरीके से क्या बातें हो रही है, राइट? Okay. So this is my input and this is my 20 liter and this is my output, guys. And it has the tan output, maybe this is the tan back mixing, and this is my PFR plus CSTR. We will try to design this 20 liter non-ideal reactor with the help of this ideal reactor, because we are aware about the ideal reactors. This is my input. So this is so obvious that input is same, and for same input, if I am getting the same output, then I can say that these systems are equivalent. These systems are equivalent. So let's say we will basically try to understand it, right? So let's suppose it is my 10 liter and it is my 10 liter. So with 10 liter plus 10 liter, let's suppose I am getting back mixing 30. I'm getting this back mixing 30. But what if this back mixing is 30? Can you say that 10 liter PFR plus 10 liter CSTR combination is equivalent to this 20 liter non-ideal reactor? You will say no, because here output are not same. Whatever you will get the output, that will not be the same, guys. Yes or no? Let's suppose that is my O1 and this is my output O2. I want less back mixing. I want less back mixing. 30 back mixing. I don't want to 30. I want to less back mixing, guys. So for that purpose, what should we do? What should we do? Less back mixing के लिए. Now the CSTR components, more the CSTR components means it increase the back mixing. It increase the back mixing. And more the PFR content, more the flow pattern is behaving like the PFR. It means the less back mixing. It means we should use like a combination, like, okay, increase the volume of the PFR, like let's suppose it's 30 liter, and decrease the volume of the CSTR, let's suppose it is 7 liter. So now I decrease the volume of the CSTR, it means you decreasing the back mixing. So let's suppose in this case my back mixing is your, let's suppose 15. In that case, in that case also we cannot say that this is the right combination. That okay, 13, use a 30 liter PFR, 7 liter CSTR, that will give you the same results as this 20 liter non-ideal reactor. We cannot say. Right? Now, what we will do? We have to further reduce the volume of the CSTR. Let's suppose it is something like that, guys, that it is my 15 liter and it is my 5 liter. In that case, let's suppose this is my back mixing instead. Now, stop it. Stop now. This is the right combination for you. If you are using the 15 liter PFR, 5 liter CSTR, that the case, this is my 15 liter, this is my 5 liter, that is the case, you can say, yeah, this is now the, you can say, actual combination of the ideal reactors for the non-ideal reactor. Clear? This, in this case, I can say this O1 is equal to O2. Guys, बहुत मेहनत की है आपको समझाने के लिए. Please let me know that these things are clear to you or not. These things are clear to you or not. बोलिए. And these are the things which you basically cannot get from the books. Book पढ़ के भी ये चीजें आपको समझ में नहीं आएंगी कि these, what is the context and all that. So that's why I'm saying that just listen me carefully, right? And I'll say that every concept will be like कि आपको लगेगा कि हाँ बहुत easy हो गया है, बहुत easy हो गया concept. Is it clear to you? Okay. So I can say by all these matter, I can say that the performance of non-ideal reactors is actually replica of ideal reactors. Replica of performance of ideal reactors, right? Is it clear to you? Is it clear to you? I hope that this thing is clear to you. Okay, done. So let's suppose I'm saying that I have a non-ideal reactor. I have a non-ideal reactor for some input and some for output. I'm getting the performance means here the performance means basically the concentration versus time graph. Okay. Let's suppose this is my concentration at the y-axis and time at the x-axis. Okay. And I am getting the concentration pattern for the non-ideal reactor is like this. Like this, right? Is it clear to you? Now this is the equivalent to the combination of the PFR and the MFR for the same input, and we want same output. Let's say when we will say same output, let's suppose in the first combination like 10 or 10 liter plus 10 liter, I will get the performance of these combinations like this, is like that for the combination 1, right? For the combination 2, let's suppose it is the performance of this combination is something like that, right? When you get the right combination, guys, then you will achieve the same pattern of the performance which is we are getting in the non-ideal reactor. So you are getting the same output or same performance in the as the non-ideal reactor performance. That's why I'm saying that performance of the non-ideal reactor is nothing but is the replica of the performance of the ideal reactor. I hope that this thing is clear to you. I hope that this thing is clear to you. Yes or no? Is it clear to you? Is it clear to you? I hope that I am very clear to you. Boliye. If this is clear to you, then please let me know so that we can move ahead. Can we move forward now? Boliye. Can we move forward now? Okay. Okay. Now understand. So these are the difference between the ideal reactor and non-ideal reactor. In the ideal reactor, we have an assumption that every molecule has an equal residence time, and in the non-ideal reactor, the residence time is different actually. So what are the reasons why the molecules cannot spend the equal residence time? What is the problem? Kya problem hai? Yes. So we will find those reasons, the reasons basically due to that your molecules cannot spend the same residence time, right? That is called your cause of non-ideality. So please put the heading cause of non-ideality. What are the cause of non-ideality? Okay. Cause of non-ideality. Let's understand this. What are the causes? What are the causes of the non-ideality? First cause of the non-ideality is my bypassing. First cause of the non-ideality is my bypassing. Right? So what I'm trying to say, guys, I'm saying this, that let's suppose this is my reactor. Let's suppose this is my reactor. Okay. Let's suppose this is my reactor. And this is the input stream. And this is my output stream. Reactant molecules are coming through the input stream. Reactant molecules are coming through the input stream. And by some reasons, this basically molecules bypass. And it is directly going into the output stream. It is going into the output stream and it is basically away from the, you can say, reactor. So this is basically your, by some reasons, your some molecules is basically bypass. So you can say that due to this bypassing, whatever the reasons, due to this bypassing, molecules molecules don't have the enough time to spend within the reaction. If they will not spend the enough time, how they will convert? They will not convert at all. Is it clear to you? So that's why non-ideality do not favor the conversion. Non-ideality always oppose the conversion. Due to the non-ideality, we will get the less conversion actually. Is it clear to you? Yes or no? So bypassing means if any, by some reasons, as you know that the agitator is there is a back mixing, right? So any molecules is basically somehow can go into the output stream. So the time spent by the molecule within the reactor is very less. It is very less. Is it clear to you? Second is my turbulency. Second reason is turbulency. Right? So in the turbulency, this is, let's suppose, my reactor. This is my input. Right? And this is my agitator. So agitator is basically mixing your mixture. So it basically form a vortex. Let's suppose some molecule is basically trapped into that vortex. If it is trapped into the vortex, then it is moving round and round and round and round. Is it clear to you? Then it will leave the reactor after so many times. So it will leave the reactor after so many times. Is it clear to you? Because why? Because it is trapped into the turbulency. घूमता रहा बेचारा एजिटेटर के आसपास ही घूमता रहा. After some time, it is basically leaving the reactor. Is it clear to you? Very best example, in the sink, if you pour the water into the sink, then a vortex is formed. Let's a piece of paper you will put to the vortex, then you will see that that paper is do not go into directly into the your sink wala pipe, है ना, vent pipe में नहीं जाएगा directly. That will rotate, that will trapped in the vortex, है ना. तो जब तक पानी खत्म नहीं हो जाता तब तक वो vent pipe में नहीं जाएगा. Is it clear to you? So due to the turbulency, what will happen? Due to the turbulency, my molecule is basically spend more than the required time within the reactor. Right? So due to the bypassing, the time spent by the molecule is very less. and due to the turbulency, the time spent by the molecule is more than required. Third reason is my dead zone. Third reason is non-ideality. Third reason about the non-ideality is my dead zone. What is the dead zone? So this is my reactor, guys, and this is my output. So this is my input and this is my output. These are the corners. These are the corners. If some molecules is trapped into these corners, then it may be possible that these molecules cannot leave the reactor. It is basically you can say trapped in the corners. It is trapped in the corners. Corner में पड़े हुआ molecules है वो कभी बाहर ही नहीं आने वाला है. वो बाहर आएगा आपको after the infinite time. It will leave the reactor after infinite time. So due to the dead zone, the time spent by the molecules, some molecules will be infinite. Right? So you can see in the dead zone, the molecules are trapped into the corners. So you can say to avoid the dead zones, basically try करते हैं reactors को round बनाने की. यहाँ से round बनाने की कोशिश की जाती है, so that the less dead zones are created. Yes, is it clear to you? So these are the some basic reasons for the non-ideality. Non-ideality means why the molecules do not spend the same time. These are the points, guys. These are the points. Bypassing, due to the bypassing, very less time they spend. Due to the turbulency, it is more than required. In the dead zone, time spent is infinite. Is it clear to you? So all these non-ideality you will find in the MFR. Right? All these non-ideality like bypassing, like turbulency, like dead zone, these the non-ideality you will find only in the MFR. You will not find in the PFR. Why? So you can say that there is no non-ideality in PFR. Right? Why, sir? What is the reason behind it? The reason behind it is, first, its flow pattern. Its flow pattern is zero back mixing. Zero back mixing means the velocity profile for the PFR is flat. The velocity profile for the PFR is flat. Means molecule only go in the straight forward direction, only in the forward direction. There is no chance of the backward direction. So there will be no chance of the bypassing. There is no agitator. Only flat velocity profile is there. So there is no chance of the turbulency. And due to the round shape, the shape is uniform throughout in all 360 direction. Due to the round space, due to the round structure, the dead zone will not be created. Dead zone will not be created in the PFR. That's why there is no known ideality in the PFR. Only the known ideality is in the MFR. That's why if you will say PFR, then there is no issue. To represent the ideal reactor, if you say that's a plug flow reactor, I'm okay with it. But in the MFR, you have to specifically mention that it is ideal MFR or it is only MFR. Right? There may be chances that you are saying the MFR that having some known ideality into it. I hope that you are grabbing the concept, what I'm trying to say, guys. Is it clear to you? इसलिए आप बुक्स में भी देखना, उसके बहुत सारे नाम्स हैं, बहुत सारे नाम है उसके अंदर बहुत सारे नाम है, उसके अंदर कहीं ना कहीं आइडियल भी लिखा होगा आगे, कुछ एक दो नाम के आगे आइडियल भी लिखा होगा, आइडियल CSTR काइंड ऑफ, राइट? So there is no chance of the known ideality in the PFR. Whatever the known ideality we will see, that we will in the come in the MFR. Is it clear to you? Boli, please say. Please say. Hanji, okay? Done? Okay. Okay. So I hope that all the things are clear to you. Now, we will have a very short discussion for the performance curve, but in the next class we will have, or in the next to next class we will have a detailed, you can say the discussion of the performance curve, right? So just you can put the heading performance curve. Performance curve. So we will try to write the performance curve for the non-ideal reactor. So what I'm trying to say that this is your non-ideal reactor. Say, let's say this is your non-ideal reactor, right? So this is your input and this is your output. This is your output, okay? This is the input and this is your output, correct? So what you have to do, just this is your detector, let's suppose. So at this detector, just you have to write the concentration versus the time. So at the time T1, what is the concentration? At the time T2, what is the concentration of your the product in the output stream? What is the at what time? What is the at time T3? What is the concentration, like that? So you will have the concentration versus the time data. If you will have the concentration versus time data, then just you can say draw the graph between C and T. Graph between C and T. So the performance curve is generally between C versus T. It is generally from C versus T. So in the non-ideal reactor, the performance curve you will find is something like that. It is something like that, guys. It is something like that. Okay. It is something like that. Sir, why this is something like that? It can be this, it cannot be this, or any other pattern. Yes, the other pattern can also be possible, but as I already told you that non-ideal reactor is something kind of experimentation thing. So in the most of the cases, this kind of pattern we will get. That's why we will discuss this pattern only. Okay? So only in our syllabus, only this pattern we will study. Okay? Is it clear to you? बाकी तो एक्सपेरिमेंटेशन का you can say कि एक चीज है, तो वो तो आप एक्सपेरिमेंट करें, फर्दर डिफरेंट कर्व प्लॉट करें और उनको स्टडी करें. दैट इज अ डिफरेंट पार्ट. ठीक है. बट फ्रॉम द गेट पर्सपेक्टिव, इन द गेट you can say in the BTech curriculum, this kind of pattern we have to study. So this is my concentration versus the time graph, and for now I will call it as a performance curve. Further I will call it with other name, that is different story, but for now I'm calling it as a performance curve, right? And this kind of the curve I'm getting. And there's a different meaning of this your curve. What is that? Okay, understand. So one thing is that here you can see that this blue thing is you are getting concentration after some time, right? Mark 1 point. Okay, and you can say that second point is that up to this, whatever this time is, let's suppose it is my time t1, and let's suppose this is my time t2, right? And let's suppose this is my time t3. Okay, this is my time t3. So this is your first zone, and in this first zone we will say one thing, we can say one thing, that the molecules up to this spend very less time within the reactor. As you can see, if you compare the T1 to T2 and T3, this T1 is very less as compared to the T2 and T3. So up to this, whatever the molecules we are getting, जो आप ये peak देख रहे हो, this is increasing concentration graph, means at the up to the T1 time, these molecules are basically spend a very less residence time within the reactor. So this zone is basically representing the bypassing, because due to the bypassing, the molecules spend a very less residence time within the reactor. If we will talk about the T1 and T2, most of the molecules exiting to the reactor between the time T1 and T2. Let's suppose I'm saying, guys, I'm saying that out of the 100 molecules, if I'll say that 60 to 65% of the molecules leaving the reactor between T1 and T2. So this zone is basically called average residence time. This is the basically zone of the average residence time. If when we will calculate the average residence time for the molecules, then for sure that time will be lies between T1 and T2. A simple सी बात है, अगर most of the molecules इसी time interval में exit कर रहे हैं, तो वो जो average आएगा उस time का, वो in between T1 and T2 ही आएगा. That must be between the T1 and T2, because major portion of the graph will be in between the T1 and T2. Okay, between the T2 and T3, it is basically representing the turbulency, because due to the turbulency, the time spent by the molecules is basically greater. Now, again, this is basically long tail. This is basically the long tail, and it is, you can say, you can extend this long tail up to the infinity. What it says, if it touches to the x-axis, it means every molecule is exiting to the reactor. But it is parallel to the x-axis and it is a long tail. It means the molecules are trapped in the dead zone. So the molecules which are trapped in the dead zone cannot go out to the reactor in a specific time. They spend the residence time within the reactor, you can say, infinite time. So this long tail is basically representing the dead zone. This long tail is basically representing the dead zone. So you will get a question in the gate PYQ. One question is they asked, I don't remember the year, that long tail of the performance curve will represent the out of the bypassing, average resistance time, turbulency. That answer will be the dead zone. So this long tail represents the dead zone. I hope that this thing is clear to you. Bolo, yes or no? Yes or no? Yes or no? Okay. Right. Now, also see, every molecule spends a different time. This is very obvious for us. Like if you see here that molecules, these concentration molecules spend this much time. This concentration molecules spend this much time. So you can see here, guys. You can see here that there is a distribution in the time. There is distribution in the time, or you can say there is a distribution in the residence time. There is a distribution in the residence time. If there is a difference or there is a distribution, so that आगे चल के हमें we have to calculate the average residence time, because when there is a distribution, in that case only we will calculate the average. In the ideal reactor, it is only one time up to the one time. If it is 3 hours, then every molecule spend 3 hours. They will get out of the reactor. There is no distribution in the time. So at 3, you will only get a one line in the ideal reactor. But in the non-ideal reactor, you will see in this graph that you will get a distribution in the residence time. I hope that this is clear to you. Right? So first, what we see, we see that that non-ideal reactor is nothing but it is a reactor in between the ideal reactors, or we can say this is a combination of the ideal reactors. When I pick one parameter, that is the back mixing, right? Why it is difficult to design the non-ideal reactor? Because we do not have the time data. We do not have the time data for the molecules, because due to the non-ideality. Right? We don't have the time data. Is it clear to you? So for the designing purpose, we will try to build or we will try to find a new way so that we can comment on the residence time of the molecules. If we are able to comment on the residence time of the molecules, then I think we will be able to design the non-ideal reactors. तो हम non-ideal reactors को design कर पाएंगे. I hope that this is clear to you, right? So that to comment the residence time to what is that new way? That way is basically tracer experiment. So we will do some experiment onto the reactor so that we can comment on the residence time, or you can say the average residence time, because there is a distribution in the time. That's why we have to calculate the average residence time. Right? So what is that way? How to perform it, or through this how we can comment on the time? We will see. Right? So I hope that chronology will be clear to you. First we pick the back mixing. After that we are commenting on the your residence time. Right? Okay. So just put the heading as tracer experiment. Tracer experiment. Tracer experiment, right? So tracer is, what is tracer? Tracer is nothing but it is a third party chemical, right? It is a third party chemical. It is a foreign chemical, you can say, right? ऐसे मत बोलना अंग्रेजों का chemical है, right? Tracer means a foreign chemical. Or third party chemical means there is a nothing lena dena to the chemical reaction, right? There is no correlation of the tracer for the reaction, right? Is it clear to you? So this is my, you can say, foreign chemical. Okay. Now, what is that eligibility, or what are the points so that any chemical can be the tracer? So let's discuss that eligibility. So put the heading criterion for tracer. Right? It's nothing like that. Every you can say chemical can be the tracer. No, there are some criteria, you know, and based on that you can say that yeah, this is the good chemical to be a tracer. First one is my chemical inert. First property of a inert for tracer is it should be chemically inert, right? And it is mandatory, yeah. It is mandatory, right? If it is chemically active, then it spoil my product. मैं एक्सपेरिमेंट कर रहा हूं, आई एम डूइंग एक्सपेरिमेंट, व्हाई? टू कमेंट ऑन द residence time, right? I'm not doing the experiment to spoil my product, to spoil my reaction. If any chemical is chemically active, then it can react with my reactants, it can form any product that is wastage for me. Is it clear to you? Yes or no? So ये तो उल्टा नुकसान हो जाएगा. I think this is not the good option that we choose the tracer which is chemically active, which can spoil our whole reaction, guys. है ना? बनाने चले थे क्या, बन जाएगा क्या, right? So my chemical should be chemically inert. Is it clear to you? Second is why it is easily available. Yes, it is easily available. It's nothing like that कि हमें जो है अफ्रीका से इंपोर्ट कराना पड़ रहा है ना. that also not the good option, है ना, because we have to see the cost also. Easily available होना चाहिए. Third one is easily miscible. Right? Easily, what is the you can say the benefit for easily miscible? If it is easily miscible, easily miscible, then it is, you can say it is if it is easily miscible, then it is easy for us to basically deduct the, you can say, the tracer. What I'm trying to say, just hold on, let me try to understand you. It is easily deductible. It is easily deductible. Fifth point is it should not stick to the reactor wall. And sixth one will be easily separable. See, now one by one point we will discuss those points. Up to this easily available, it is okay. So basically we will try to comment on the residence time of the molecules. For that purpose we basically add a tracer. Tracer is an inert. So first of all it should be deductible, easily deductible. अगर वो easily deductible नहीं होगा तो हमें, you can say कि easily अगर deductible नहीं होगा तो फिर आप कैसे residence time पे comment कर पाएंगे? So we make sure that the tracer is easily deductible and it should not stick to the reactor. Okay, and it is also easily separable, because the inert present in our product is not good for us. It basically decreases its purity, it decreases its concentration, and if it will not miscible into the reacting mixture, then we cannot comment on the reacting molecules. Is it clear to you? That's why it should be easily miscible into it, right? If it is not easily miscible into it, then for the miscibility, it may be possible that we have to add the third component. That also includes the complexity in our reaction, right? So these are the basically criterion for the tracer, that chemically inert, easily available, easily miscible, easily deductible, because we basically comment on the residence time after deduction of the tracer. Tracer को deduct करेंगे outlet पे. We basically deduct the tracer at the outlet stream, right? And okay, and easily separable and all that. I hope that all these points are very clear to you. Yes, guys? These points are clear to you or not? Please tell me. Please tell me. I'm giving you more clarity onto it, right? Just hold on. बाकी यहां तक आपको समझ में आया या नहीं, प्लीज बताओ. या इट मे बी कह सकते हो कलर तो डिडक्टेबल ही हो गया. किया कलर मींस डिडक्टेबल. लो कॉस्ट यस. नॉन रिएक्टिव मींस इनर्ट. नॉन इनर्ट एंड रिएक्टिव मींस same thing. Non-reactive and inerts are the same thing. Low cost, yes. So every the like easily available means the cost will be low. The cost ज्यादा add हम ना करें import export वाला. ठीक है. Now let's discuss more things. How basically this tracer help us to figure out the residence time of the molecules. So let's suppose, guys, that see what is the meaning of the residence time. Residence time means like you are, let's suppose you are going to the library for the gate preparation. That library, that closed room is a reactor, and all the students are the molecules. So you basically enter to the library, means the molecule enter to the reactor. You spend some time within the reactor, right? Or within the library. After that, basically you leave the library. So the time you spend within the library, that is the residence time. That is the residence time. Is it clear to you? Okay. Let's suppose we have a school classroom. Let's suppose this is the school classroom, and there are two gates for the entry. One is for the entry and one for the exit. Let's suppose this is the one way to get into the, this is the entry, and let's suppose this is the exit. This is the exit, right? Let's suppose we have 100, let's suppose 1000 student. We have 1000 students of a one school, and school has a one uniform. Uniform means all the pant and shirts is the same color and all that. So all those 1000 students are very similar. It is very similar. If thousands of the students get into the library and that get out into the library, then it is, I think, very it is quite difficult to figure out that which students spend how much time in the library. कोई जाके कोने में यहाँ बैठ जाए, कोने में यहाँ पे बैठ जाए और वो बताए ना, हमें पता नहीं लगेगा. If I am getting the 999 out of the 1000, then what matters? It hardly matters. पता भी नहीं लगेगा कि एक स्टूडेंट गायब है. Even in the 1000, if 10 are missing, then it is quite difficult to figure out that 10s are missing. So it is quite very difficult for us to get the time data, that कौन से student particular, which students spends how much time into the library. So it is the 1000 students wali baat. If it is comes to the mixer, then it is a millions of the molecules. So it is very difficult for us to get the value of it, right? Is it clear to you? So you can see your uniform wale bacche is your reacting mixture. Now what I will do, I am injecting a tracer which is easily miscible. Easily miscible means that let's suppose this is the row of the students. These are the row of our students. If it is the miscible, then it can occupy a space in between the students. So let's suppose this yellow color is a This, let's suppose this color is basically of your tracer. I inject the 1, 2, 3, 4, let's suppose 5. I inject 5 molecules into the 100 students, right? So it has some, I shows the different color. Why? Because I'm saying that it is easily deductible. Why I call it as easily miscible? Why? Because it can occupy in between space, right? Is it clear to you? So this tracer, I'm saying this tracer to, okay, काम करना हमेशा इस स्टूडेंट के साथ रहना, stick to this student. I'm saying to this, stick to this student. I'm saying this to stick to this student, like that. Is it clear to you? So बच्चों की ट्रेन देखिए ना, पीछे पीछे शर्ट पकड़ के चलते हैं, ट्रेन आई, like that. So these are entering into the, and this is, here I'm injecting the tracer. I know at what time I'm injecting the tracer. So at what time these tracer molecules entering into the reactor, I know this, right? And these are the easily deductible. So at the outlet time, I know that at what time these molecules are out from the reactors, right? Is it clear to you? And these are the easily separable. These are easily separable. So ये separate भी हो जाएंगे इससे, और product अपना बाहर चला जाएगा, और मुझे उनके residence time की information मिल गई. So these are the kind of spy. Yes or no? Is it clear to you? So guys, this is how a tracer will help us. This is how a tracer will help us to get the values of the residence time. And why I write these property, I think now you are very clear with that why these properties are important for a chemical to be a tracer. Please let me know that these things are clear to you or not. Please say, this should be crystal clear to you. Okay, so guys, आपका जो आज का empty lecture था, mass transfer lecture था, so today's empty lecture is rescheduled for the tomorrow, and the timings will be 6 a.m. to 8 a.m. Okay, the empty class timings will be 6 a.m. to 8 a.m. ठीक है, tomorrow, right? So आज वाली जो क्लास है पोस्टपोन हो गई है, ठीक है. टुडेज क्लास विल बी पोस्टपोन गाइस. So guys, I think for the today's class, that's it for the today's class guys. Just revise it, just go through it, what I'm saying, whatever जो भी आपने लिखा, मेरे बोलते बोलते टाइम लिखा, या जो भी आपने यहाँ स्लाइड से लिखा. So basically just revise it guys, just revise it, right? And in the next lecture we will discuss it further, the tracer experiments with mathematical expressions and all that. Okay, so I hope that you gain some information. Okay, you gain some 5-10% increment in your knowledge. So chaliye fir, thank you so much, bye bye and take care. We will meet in the next class. Hopefully in the tomorrow's class we will discuss the further things. Okay, so chaliye, ठीक है, bye bye and take care guys. Okay, let's meet in the next class. Bye and take care. If you have any problem, drop a message in the group.